Hello everyone. In this video, we're going to go over the Chapter 4 exam review. As a reminder, I know the test review says 1055. This also applies to Math 1050. So first up in this exam, we're going to convert equations. Now, this is a big part of this chapter. It's going to show up a lot. And this is part of the idea that logarithms are the inverse of exponentials. So first we're saying convert e to the sixths equals x to logarithmic form. Well, remember the logarithm base e is the natural log, so we would say natural log of x equals 6. So notice that the input of the exponential becomes the output of the logarithm, and the output of the exponential becomes the input of the logarithm. This is the inverse idea that we're switching x and y. Similarly, when we convert log base 6 of x equals 3 to exponential form, that becomes 6 to the third equals x, because x is the input of the logarithm, and now it's the output of the exponential. Another way you can think of it is that I've heard this called the crazy cucumber or telephone method, where you recognize that the 6 to the third is going to equal x. Now for c, we get something similar. I'm going to put log base 7 because it's a 7 to the x power of 23 equals x. And then for the last one, 7 to the x equals 3, because once again, my input becomes an output and my output becomes an input for each of them. All right, let's practice with some log properties next. We're going to expand this logarithmic expression. Shouldn't have an S there. Now, remember, this comes from our log properties, that the log of a sum, or excuse me, the log of a product is a sum of logs. A log of a quotient is equal to a difference of logs. And a log of a power is the same as r times log of x. Now, let's apply these all together. So I notice I have an x to the fifth times y to the third over a w to the fourth square root of z. So that means all my multiplications can become addition. And then everything that's divided, everything that's on the bottom, becomes subtraction. Now, we're almost there. If we want to expand it completely, I need to take off those powers from the inside. So this becomes 5 natural log of x plus 3 natural log of y minus 4 natural log of w. Now, how do we get rid of the square root? Remember that a square root is the same as a 1/2 power. So this is minus 1/2 natural log of z. The next question is just asking us to do that backwards. And so this 7 is going to go in as a power on z. This 8 is going to go in as a power on x. This 1/5 is going to go in as a power on y. And so we end up with log of z to the 7th, and then everything positive ends up in the numerator of my combined logarithm. So z to the 7th, x to the 8th, divided by the 5th root of y. Now, where did the 5th root come from? The 1/5 power is the same as the 5th root. All right. Now we're going to take a step back and graph exponentials by using our exponential transformation properties. So how is this a transformation of 4 to the x? Well, since there's a minus 2 on the x, we move right 2 and the minus 3 is down 2. Remember everything, or down 3, excuse me. Remember, anything done directly to the x is the opposite of what we expect. Now, what does that mean for the domain and range and equation of the asymptote? Well, the domain for any exponential is all real numbers. So it doesn't matter what the equation is, its domain is always all real numbers. So let me make a note of that, all exponential functions. Now, the range always depends on the vertical transformation. Normally, a 4 to the x, its domain, or excuse me, its range is 0 to infinity. However, since we moved down 3, my range must move down 3. So my range is from -3 to infinity. And that means my asymptote is a horizontal asymptote at y equals -3. So let's draw that. Here's my asymptote at y equals -3. And how do I find some points on that? Well, in the original 4 to the x, so I'm going to use I'm going to use purple for the original f of x equals 4 to the x. I know I have the y-intercept at 0, 1, and then it goes to the point 1, 4, and grows really fast. And if I need an extra point, I know it goes through -1, 1/4. And so it looks like this. Now I get to move all those points over 2 to the right 2 and down 3. So this y-intercept moves right 2 and down 3. One thing I always notice is that the y-intercept, no matter where it moves, is a point that is 1 above the asymptote. And then this point moves, and then the point of 1, 4 moves over 2 and down 3. And I can double check. Do I go, whoops, I apologize. I just noticed I plotted that point at 1, 5. Silly me. This is why you check your work. So that point on the original is now at 1, 4. And so in the other one, it is now at 3, 1. And that -1, -1/4 is going to be at 1, -2 3/4, because it's just 1/4 above the asymptote. And then I draw the picture. Now, is that completely accurate? No, absolutely not. I do not need perfect graphs. That's what computers are for. Your job is to plot some points and the basic shape so you know what this graph should look like when you put it into a calculator or computer to graph it. Okay, now let's do it backwards with the inverse function. So g of x, it's a translation of f of x up 4 units and to the right 3 units. Well, to the right 3 units, that means I have log base 3 of x minus 3, and up 4 units, hey, that's a plus 4. And so we would say g of x equals log base 3 of x minus 3 plus 4. And now we're going to do all the same things we did with the previous one. We'll do domain, range, and asymptote. Now, since logarithms are the inverse of the exponential, instead of their domain always being all real numbers, it's their range that's all real numbers, because it's the inverse. Now, the domain depends on the horizontal shift. Well, how far was I shifted? I was shifted 3 to the right, so my domain is 3 to infinity. Another way I can check that is the inside of a logarithm must always be positive, so I can always solve the inequality x minus 3 is greater than 0 just to double check. And I add 3 to both sides, I get x is greater than 3, and everything's hunky-dory. Now that means our asymptote must be at x equals 3. And notice it's a vertical asymptote, whereas for the exponential it was horizontal because it's the inverse. All right, now let's move on to graphing. My asymptote's at x equals 3, so I'll put it there. And so now how do I plot g of x? Well, I know the original is log base 3 of x. You don't have to plot the original, but it's helpful. And I'm going to plot it. I know it goes through 1, 0. All logarithms go through that point because log base anything of 1 is 0. And then the next good point I know is 3, 1 because log base 3 of 3 has to be 1. And I'll go ahead and draw that. I know that logarithms grow very slowly. Now let's do the inverse. I'm going to take all the points I know and move them to the right 3 and up 4. And so notice that's 1 away from the asymptote, and the next one should be 3 away from the asymptote because it's base 3. And so now I have my nice logarithm. Once again, is that perfect? Could I use this to figure out what log base 3 of 4 is? No, this is not perfect. That's what computers are for. I just want you to know the basic shape, what it should look like, so you can detect errors when you write these in a computer. All right, now let's solve equations. So when we solve exponential and logarithmic equations, our general strategy is isolate the weirdness. So that's our exponential and logarithm, and then get rid of it. So here, I'm going to make it so I just have the exponential on one side. The one problem I have is I have this 6 right here. So I need to divide both sides by 6. So I have 5 to the x equals 12. Now, why did I have you switching forms? Because we use it to solve equations. I'm going to switch forms here. I'm going to make that 12 the input of a logarithm base 5 and that x the output. Now, this is an exact solution. However, with a normal scientific calculator, most of them can't do log base 5. And so remember, you could also do natural log of 12 divided by natural log of 5 in a scientific calculator to figure out an approximate value, because that's our change of base formula. So that's not too bad. So let's make it worse. So over here, part of the problem is I have 2 e to the x's. So just like we would do with solving for x, I'm going to gather all my e to the x's on one side. So I'll subtract 5e to the x from both sides. I end up with negative 8 equals 2e to the x minus 26. Once again, I'm going to isolate the weirdness, the exponential. I'll add 26 to both sides. And I get 24 equals 2e to the x. I'll divide by 2. So I get 12 equals e to the x. And now I can switch that to logarithmic form. So that 12 becomes the input of a logarithm, and that x is its output. So I know that the answer is natural log of 12. Now we're going to do the same thing with the logarithm. This is ln, and so to switch it to its exponential form, I need to take the input and have it be the output of an exponential of the proper base, which is e, because it's a natural logarithm. Now you may wonder, why do we talk about natural logarithms so much? Calculus. They're used all the time in calculus because they have some really nice properties. So now I'll subtract 1 from both sides. I need to get x equals e to the 13th minus 1. And that's our answer. So let's make it harder. Here, the problem is that I have two logarithms, so I need to somehow combine them. Now, we can't just add their insides because logarithms aren't multiplication. I can't distribute them. But I can use logarithmic properties and say, hey, an addition of logarithms is the same as a logarithm of a product. So now I've isolated my logarithm. I've made it into one thing. And now I can switch forms to get rid of it. And since this is log base 2, I end up with x minus 3 times x minus 7 equals 2 to the 5th power. The input of the logarithm became the output. The output became an input. Now let's multiply some things out. The x minus 3 times x minus 7 ends up being x squared minus 10x plus 21, and 2 to the 5th is 32. Now, how do we solve quadratics? We always get 0 on one side. I often joke that 0 on one side is like the athletic stance they teach you in sports or high school gym, where you can do a lot of things from there. If needed, you can factor, you can do the quadratic formula, complete the square. It's just that 0's the hero when it comes to quadratics. So I end up with x squared minus 10x minus 11 equals 0. And let's check if that's factorable. We want to know, are there two numbers that multiply to negative 11 and add to negative 10? Hey, there are negative 11 and positive 1. So that means this factors into x minus 11 times x plus 1 equals 0. And so my answers are 11 and negative 1. However, we want to double check. So here's the issue. The issue is this negative 1. Let's see what happens when we put it in for x. In the original equation, I get log base 2 of negative 1 minus 3 plus log base 2 of negative 1 minus 7. Sorry, let me rewrite that. Negative 1 minus 7. Now this is an issue. We can't have negatives inside a logarithm. So this is an extraneous solution. Whoa, that was strange. All right, now let's do something similar in a more applied context. So a certain population of wolves can be modeled by the equation f of t equals 1,000 e to the negative 0.11 t, where t is the time in years since 2024. So this is something that biologists actually use. They use more complicated versions, but this is a basic version of a population model. So is it increasing or decreasing? This is actually decreasing. How do we know? There's a negative exponent. This is one thing we like about, instead of doing this as like 2 to a power or 1/2 to a power or something like that, we like e because, one, if it's a negative exponent or a positive exponent, we can tell if it's increasing or decreasing. And the other reason, calculus. Now, the next thing we need to do is determine how many wolves this model predicts there will be in 2035. Now, notice that this is time in years since 2024. So that means I need to do 1,000 e to the negative 0.011 times, well, what's 2035 minus 2024? Oh, that's just 11. So I need to put 11 in for my time. Now, that's not something you or I can do in our head. Well, maybe you can if you are amazing, but I am not that amazing. So I'm going to plug that into a calculator off screen. And so what that gives me is this really long decimal. But I can't have a decimal number of wolves. That doesn't make sense. And so we'll round it. Okay, I get to edit this out because, oh, that's why. La-di-da-di-da-di-da. I should have grabbed a better calculator. So my calculator, I'm sorry, let me do the snap thing. So my calculator says that this is approximately 886.033959593. But that doesn't make sense. So we'll say about 886 wolves. Unless you want to think of that 0.03 as maybe there's a female that's pregnant with one, but not very far along, but 886 is what we would say. So when will the population of wolves reach 500 wolves? Hey, that's an equation to solve. So I have 500 equals 1,000 e to the negative 0.011 t. And we solve just like we did the other ones. I divide by 1,000. So I get 1/2 equals e to the negative 0.011 t. I'm going to switch forms. So I get natural log of 1/2 equals negative 0.011 t. Now, natural log of 1/2 is just a number. It's a weird number, but it's just a number. I'm going to divide that number by 0.011 or negative 0.011. And that tells me that t is going to equal natural log of 1/2 over negative 0.011. Once again, that's not something I can figure out in my head. Excuse me. So I'm going to plug that into a calculator. And so natural log of 1/2 divided by negative 0.011. It gives me this weird decimal that's about 63. But it says, when will it do it? Well, what's 63 years from 2024? That's 2087. Now, if you want to look at a real situation where people had to do modeling like this, or maybe they should have, you can look up about how wolves were reintroduced to the Yellowstone ecosystem. Now, let's look at another application, which is compound interest. So we're going to have a compound interest problem where we start with $10,000. Remember, that always just goes on the outside of an exponential because that is our starting value, our principal. And then we have 1 plus to represent it's growing. We put in that 4% as a decimal. And then since it's monthly, I divide by 12. And then I do to the 12 times t. That's what the month, that we put 12 because it's monthly. And so our general formula that you'll see in textbooks or whatever is our P naught or P0, that's our initial value, 1 plus our percent rate divided by the number of compounds in a year, with the number of compounds times t. And now I want to know how much is in the account after 30 years. Well, I'm going to put 30 in, and I'll do 10,000 times 1 plus 0.04 over 12 to the 12 times 30 power. Now, I don't know about you. I can't do that in my head. And so I'm going to, once again, plug that into a calculator. So I get 10,000 times 1 plus 0.04 divided by 12 raised to 12 times 30. I know 12 times 30 is 360, so I sometimes just go ahead and put the number of, like I just put 360 in there. Now it gives me a big long decimal, but it ends up being about 33,134.98. Now, notice in 30 years this amount tripled. This is why when people talk to you about planning to retirement is to save early, because this is how compound interest helps you. And if you're saving in the right type of account, a 4% interest rate is actually kind of low. And so it's easy to save up a lot of money over a long time if you start early. All right. Let's talk about half-life. Half-life is how long it takes for half of a radioactive element to decay. This is a really important thing when we're talking about radioactive waste. So let's look at plutonium-238. This is the actual half-life for it. I looked it up online. So let's write a function that models the mass of plutonium-238 after t years. Now, there's two ways to do this. One way is to force E to come in there. And we know that our function should be, let's see, we start with 50 grams, so that goes there. E, and we need something times t. Now, how do we figure that out? Well, it turns out that that something is always going to be natural log of 1/2 divided by the half-life, so 87.7. I'll plug that in my calculator. And so natural log of 1/2 divided by 87.7. It's a really nasty decimal, but it's about negative 0.0079. Alternatively, the way I could do this is if I don't want E to show up, I can use the fact that this is a half-life. So if it's a half-life, it's going to get multiplied by 1/2 every 87.7 years. Well, how do I represent that? I take my number of years and divide by 87.7. So that way, it cuts it in half every 87.7 years. I like using that one a little bit more, but the E1 can be helpful in calculus situations. Now, I'm going to use this function to predict the amount of plutonium-238 remaining after 100 years, So I'm going to do 50 times 1/2 to the 100 over 87.7 power. Once again, I'll plug that into my calculator. So that comes out to, on my calculator, about 22.684 grams. Which, that's important to know. How much nuclear waste is going to be left over after so many years. Now, that may not be something you actually calculate in your work, but it may be something as an informed citizen you want to at least understand when scientists are talking about this material has a half-life of et cetera, et cetera. Now, let's find some inverses of exponential and logarithmic functions. Now, we can always find inverses using our classic strategy of flipping x and y, where I say x equals 6 to the y minus 2 minus 8. I can add the 8 to both sides. So I end up with x plus 8 equals 6 to the y minus 2 power. I've gotten my exponential isolated, so now I can switch it to a logarithm. End up with log base 6 of x plus 8 equals y minus 2. I add that 2 to both sides. And so in the end, I get that the inverse function must be log base 6 of x plus 8 plus 2. But let's notice some patterns. That minus 8 on the outside turned into a plus 8 on the inside. This minus 2 here turned into a plus 2 on the outside. So let's see if we can take advantage of that pattern for g of x. Well, we know it's log base 4, so its inverse has to be 4 to a power. That one has a minus 8 on the outside as well, so I should probably have an x plus 8 up here. And it has a plus 5 on the inside in the original, so I should have a minus 5. So you see how we're taking advantage of the pattern that they're inverses. What's on the outside goes on the inside and vice versa. Another way you can think of it is by transformations. This x plus 5 is a left transformation. In the inverse, it should be a down transformation because we're switching x and y. Similarly, actually, let me make a note of that. Left becomes down because we're switching x and y. Similarly, this down transformation of minus 8 should turn into a left transformation in the inverse. So that should be an x plus 8. So that's just another way to think of it, to check your work or do it another way. All right, we're going to finish talking about gross domestic product. That's the sum total of goods and services produced by the U.S. in a given year. And if any of you are economics majors, you may know that better, and I may have said it wrong. Don't at me. So we have this model. This represents that the gross domestic product is growing, which is good. And we want to know when the GDP reaches 11,000 billion. Now, notice the question says that the given model is already in billions of dollars. So that means I don't need to write out 11,000 billion with all its zeros. I just need to use that 11,000. So I'm going to solve 11,000 equals 9,743.77 times e to the 0.0514 t. So since it's already in billions, I don't need to expand out that 11,000. And now we solve this just like all the other ones. I start out by dividing by that 9,743.77. Now, I'm going to need a calculator to figure out that division, but I know it's going to be weird. So instead of putting a weird number in here, I'm just going to leave it as 11,000 over 9,743.77. And think of it as I'm saving that division for later. I know it's weird. I don't want to deal with the weirdness now. This is a way to help make sure our answers are more accurate. This prevents rounding errors. So now I'll take the natural log, I'll switch this to its logarithmic form. This becomes natural log of 11,000 over 9,743.77 equals 0.0514t. I divide by that fun decimal, 0.0514. And once again, I don't know what that number is going to be. I'm going to wait till the end. So I have natural log of 11,000 over 9743.77, all divided by 0.0514, and that's going to be what our time is. And so when I put that in my calculator, so I plug that all in, and I put it on my calculator before recording this just so I could get to it more easily. I get 2.359. So it's going to take about 2.359 years. But this asks what year? Well, this is between year 2 and year 3. So we'll go ahead and round up to year 3, just to think of it as we're covering ourselves to make sure we get it right. So this should be in about the year 2003. All right, I hope this video was helpful. Have a great day.